a new out-of-this-world discovery has some asking, what in the world is this? Take a look. NASA scientists say it's a comet. That's what they say. They've named it the 3-1 Atlas interstellar object.
Tonight on The Future of Everything, we've got 3i Atlas passing through our solar system. 3i Atlas has all kinds of surprises.
According to NASA, an interstellar comet, officially designated 3I/ATLAS, is racing through our solar system on a hyperbolic trajectory. This once-in-a-lifetime encounter is already challenging what we thought we knew about icy visitors from beyond our sun. In just a few short months, this object has ignited a worldwide effort across professional observatories and backyard telescopes alike, producing a torrent of fresh data, bold claims, and, inevitably, controversy. Tonight, we cut through the noise and look at what's genuinely new, what holds up under scrutiny, and why this stranger may change how we think about comets born in other star systems. I'm your host, and this is a deep dive into the 3I/ATLAS project. What it is, how we learned about it, and why scientists are both thrilled and cautious. We'll follow the evidence, images, spectra, and light curves, then examine the competing interpretations behind them. We'll also talk about the temptation to jump to conclusions when the headlines get hot, and how the scientific method handles the tug-of-war between curiosity and proof. Our story starts with a crucial distinction. 3I/ATLAS is not bound to the sun. Its path is open-ended, a flyby from interstellar space. That alone puts it in a tiny club of confirmed interstellar visitors. But unlike earlier objects that flashed by with minimal data, we're watching this one over a longer arc. That longer look brings clarity, but also reveals complexity that a single snapshot can never tell. Interstellar objects are cosmic postcards from distant neighborhoods. Each one carries the chemistry and history of a different protoplanetary disk. With 3I/ATLAS, several threads converged quickly. Activity at great distance. Even far from the sun, farther than many native comets switch on, it showed signs of outgassing. That hints at hypervolatile ices that vaporize at lower temperatures than water, such as carbon monoxide or carbon dioxide, a fast, open trajectory. Its speed and path are consistent with an origin beyond the sun's gravity well, confirming we're seeing a traveler, not a local on a strange loop. A flood of attention. Major facilities and quick-reacting survey telescopes pivoted to track it, building a record not just of where it is, but how it behaves and evolves. The big idea: this is a moving laboratory. As the comet approaches, sunlight changes what we can see. Different ices wake up, dust behavior shifts, and the coma and tail reshape, turning 3I/ATLAS into a time-lapse experiment in real physics. Imaging tells us shape, spectroscopy tells us substance. By splitting the comet's light into its component wavelengths, astronomers look for chemical fingerprints, emission features that betray which molecules are present and how active they are. Early on, the pattern pointed to carbon-bearing volatiles, especially CO and CO2, playing an outsized role relative to H2O. That makes physical sense when the comet is still cold. Carbon monoxide and dioxide sublimate at lower temperatures than water ice. As 3I/ATLAS has moved inward, observers have monitored whether the water contribution rises and how the overall balance of species evolves with solar heating. This chemical choreography matters because it encodes the conditions in which the comet formed: pressure, temperature, and processing by radiation back in its birth system. Another intriguing piece is cyanide CN emission, a classic comet tracer produced when sunlight breaks apart parent molecules such as hydrogen cyanide. Detecting CN says the engine is on, but the ratios are what fascinate researchers. How much C2 dicarbon exists relative to CN? If the C2/CN ratio is unusually low, the comet is said to be carbon chain depleted, a category that tells us something about its primordial chemistry and thermal history. That label alone doesn't make 3I/ATLAS unique. but paired with other behavior, it sketches a chemotype we rarely get to sample from outside the Sun's family. Brightness is the most public-facing metric. Everyone can appreciate it got brighter. But the why is the story. As the comet drew closer, its flux increased faster than simple sunlight distance math predicted. A big jump beyond expectation signals enhanced activity. Maybe a patch on the nucleus rotated into the Sun and ignited. Maybe dust grains are fragmenting into more reflective surfaces. Maybe gas jets are dragging dust outward more efficiently than models assumed. Think of 3 I/ATLAS as a bag of ices stitched together by dust and organics. Warm it a bit, and the most skittish molecules flee first. Warm it more, and slowpokes, like water, join the escape, pressurizing subsurface pockets, lifting larger grains, then shattering them into a fog that scatters sunlight. The net result on your detector? A surge in brightness, not always smooth, not always predictable, because real geology is lumpy and rotationally uneven. If you track a comet's brightness meticulously, you can sometimes tease out periodicity, a repeating pattern that betrays rotation. For 3 I/ATLAS, the data have been noisy and the periodic hints subtle. There are indications of a rotation period on the order of many hours, consistent with a nucleus that is neither tumbling wildly nor mirror smooth. The difficulty here reinforces a theme. Faint, moving targets test the edges of our instrument's sensitivity, and comets add extra jitter because their own activity can mask or mimic rotational signals. Even so, the emerging picture suggests a nucleus that doesn't present huge brightness swings face to face. That could mean it's not extremely elongated or that the active regions distribute light fairly evenly over a rotation. Either way, the fine print of shape is less urgent than the broad truth. A modest, active body is driving the spectacular, ever-changing coma we see. A comet's tail is a physics experiment stretched across space. 2 broad forces sculpt it: solar radiation pressure and the solar wind. In most textbook images, the dust tail streams away from the Sun, while an ion tail, glowing in specific colors, points almost straight downwind. Real comets don't always obey the diagram. Dust grains of different sizes respond differently. Some drift sunward briefly when fragmentation increases their surface area, or when gas jets loft particles into trajectories that sunlight later reshapes. For 3 I/ATLAS, successive images have shown a lengthening, evolving tail and a coma whose texture hints at changing dust physics. Aggregates breaking apart, new grains joining the flow, and light scattering that subtly reshapes the glow. Every frame you compare over days is a reminder. This is a living system responding to a star. One of the most sophisticated tools in the astronomer's box is polarimetry, measuring the preferred orientation of light waves after they interact with dust. Some comets show a positive polarization pattern, others exhibit a negative branch, light polarized parallel to the scattering plane near certain viewing angles. The depth and width of that negative branch depend on dust grain size, structure, and porosity. For 3 I/ATLAS, polarimetric observations unveiled a strikingly deep, narrow negative polarization branch. Translation: the dust is doing something unusual by way of its size, distribution, or texture compared with the comets we know best. That doesn't necessarily mean alien manufacture. It means the dust may be fluffier, more fragile, or differently aggregated, which fits a narrative of a body assembled and preserved in an environment unlike our own outer solar system. In other words, we're sampling a foreign dust ecology. At times, observers have reported a green cast to the coma, which is classically associated with C2 fluorescence, dicarbon molecules excited by sunlight. The twist is that other lines of evidence point to carbon chain depletion. Can both be true? Potentially yes, because visual impressions can be deceptive, and the comet's chemistry is time variable. A brief uptick in C2 production, a particular filter set, atmospheric conditions, or image processing can emphasize or mute that signature. The careful stance is to treat such color impressions as clues that need spectral confirmation, not final verdicts by eye. Whenever an interstellar object appears, a familiar question arrives with it. What if it's artificial? It's a question that captures imaginations for good reason. We've never had better telescopes, and first contact stories sit near the core of our cultural mythos. Some commentators and even a few researchers have floated technological scenarios for 3I/ATLAS, often pointing to early uncertain size estimates or to orbital coincidences as suggestive. Here's the discipline journalism demands. Extraordinary claims must outrun evolving data, not lag behind it. As refined images and spectra moderated the nucleus size and clarified the comet-like nature of the outgassing, the natural explanation strengthened, not weakened. Gas-driven non-gravitational forces can nudge a small body's path. Rotational torques and uneven heating can jitter its motion. None of that requires intent. The right way to treat the technological hypothesis is as a testable, falsifiable idea that must survive new constraints. So far, the constraints favor nature. As 3I/ATLAS nears and rounds perihelion, several things are likely. Chemistry will reshuffle. Expect water to contribute more as temperatures rise, potentially changing the balance among CN, C2, CO, and CO2. If water, or other late-rising volatiles, surges, the coma's brightness and texture can pivot quickly. Activity could spike, or the nucleus could fracture. Comets are sometimes called fragile, dirty snowballs. Thermal stresses, pressurized vents, or rotational spin-up can split a nucleus. Fragmentation often produces a short-term outburst as fresh ice is exposed, followed by a fade as pieces disperse. The tail may redraw itself. With stronger outgassing, dust size distributions can shift, making the tail broader, longer, or more structured with streamers and kinks where jets feed it. Post-perihelion comparisons will be gold. Measuring the comet on the way in versus on the way out reveals hysteresis. Does the same sunlight produce the same response after the surface has been stress-cracked, devolatilized, or dust-mantled? Those before-after asymmetries teach us about surface evolution in real time. We don't get to choose which interstellar objects show up. We can only choose how well we listen. With 3I/ATLAS, we're listening across the spectrum, from ultraviolet to infrared, with cameras that see shape, spectrographs that see chemistry, and polarimeters that see texture. Each technique contributes a piece: images, morphology, tail geometry, coma structure. Photometry, brightness changes, hints of rotation, outburst timing. Spectroscopy, volatile inventory and how it evolves with distance. Polarimetry, grain physics, porosity, and aggregation states. Put together, they sketch a comet that is active earlier, chemically distinctive, and dust-wise unusual. A body likely shaped in a different nursery than our Kuiper belt or Oort cloud. That's the headline beyond the headlines. Interstellar comets carry diversity. Each one we catch expands the map of what comet can mean. Science thrives on wonder, but it advances on restraint. The best way to honor an interstellar visitor isn't to romanticize it into a message in a bottle. It's to measure it so well that, if a message ever does arrive, we won't mistake weather for writing. That's what the global collaboration around 3I/ATLAS represents. Observatories sharing time, teams comparing notes, amateurs contributing sky coverage the big facilities miss. For viewers and readers, the takeaway is simple and beautiful. A new comet from another star isn't just a spectacle. It's a lesson plan in physics, in chemistry, in how fragile ice and dust can encode the conditions of alien dawns. And for a few precious months, our star's heat is the teacher and space is the classroom. As 3I/ATLAS arcs around the sun and heads back to the dark between the stars, it leaves us with sharpened tools and humbler expectations. We'll keep tracking its brightness, its spectrum, its polarization, and any structural changes that perihelion might provoke. Whether it flares dramatically or fades quietly, this comet has already given us something rare, a look at someone else's recipe for making a world. If you enjoy evidence-driven explorations like this, stick with us. We'll keep following the data wherever it leads, celebrating the mystery while insisting on the measurement. Because out there, between suns, there are more visitors on the way, and next time we'll be even more ready to listen.